See student, feel like a atom. The atom is moving along the x-axis, y-axis and z-axis. And next one, this is diatomic molecule. See student, two atoms are there. Okay, so for this also rotational motion we will discuss about it. And next I am going to form the triatomic gas like H2O. This is non-linear because of not along the same axis. This is 3D. This is the very clear tabular form about mono, di, tri, tetra, polyatomic gas, temperature, room temperature, high temperature. Next, linear or non-linear molecule with examples. Okay. Hello everybody, I am Kiran Kumar from Nature of Physics. Today topic is very clear explanation with neat diagrams and also clear diagram explanation, law of equipartition of energy. See that first, degree of freedom definition and translational degree of freedom. Next, rotational degree of freedom. And for this also diatomic, triatomic gas linear. And next one is, see there, non-linear for the explanation of rotational degree of freedom, and in which triatomic gas, tetratomic gas, polyatomic gas, methane taken CH4, and vibrational degree of freedom also clearly linear and non-linear. Vibrational degree of freedom at room temperature, high temperature, clear explanation with formulas. For law of equipartition of energy is a theory part already written clearly about monoatomic gas, diatomic gas, polyatomic gases, translation motion, rotational motion, vibrational motion, degree of freedom, energy, and also molar specific heat at constant volume and constant pressure ratio gamma, which is equal to molar specific heat ratio. Okay, so that the number of independent ways in which a molecule of a gas can move is called degree of freedom. Yes, translational degree of freedom in which x-axis, y-axis, z-axis taken. For example, this is a atom. It may move along the x-axis or y-axis and also z-axis, and three-dimensionally represented along the x-axis motion Vx, along the y-axis motion Vy, along the z-axis motion Vz. So there is a 3 degree of freedom for the translational motion. So that is translational degree of freedom Ft, which is equal to 3. Okay, clearly written there. So this is feel like a monoatomic gas molecule. Example is taken, okay, helium, argon, neon. Okay, and next one is rotational degree of freedom. So it represents the number of unique ways the molecules may rotate in space about its center of mass. So for this, first one is monoatomic gas. Monoatomic gas will not have the rotational degree of freedom because of the center of mass sit directly on the atom, so that monoatomic gas, it has no rotational degree of freedom. Fr is equal 0. Example taken, helium, neon, argon. So center of mass at the center of the atom, so it will not have the any rotational degree of freedom. For example, see, this is the helium, so it is rotating like this. See there. Okay, so center of mass at any rotation, either x-axis or y-axis or z-axis, any rotation, center of mass at center only. With respect to center of mass, there is no rotation, so radius is minimum also. Again we will discuss in the diatomic gas molecules lying along the x-axis rotation about mutually perpendicular y-axis and z-axis. Here the molecule we are considering, that is diatomic molecule. So the diatomic molecule is lying along the x-axis. See there, along the x-axis. Here also x-axis. Next also x-axis represented, and rotation is along the y-axis and also z-axis represented, and rotation along the x-axis, radius is very less. See there clearly. So this is representing x-axis. Along the x-axis rotation is equal to, okay, 0 degree of freedom considering, because of here radius is minimum, that's why moment of inertia also minimum, that's why rotational kinetic energy also minimum. We can take along the x-axis rotational degree of freedom which is equal to 0. Okay, and next here this diatomic gas molecules have rotational degree of freedom only 2, even though triatomic gas molecule, linear molecules also have the 2 degree of freedom. So diatomic molecules, it has 2 atoms. Example is hydrogen, and next N nitrogen, next O oxygen and oxygen. These 3 examples given for the diatomic gas molecules. And next triatomic gas molecule taken CO2, CS2, NO2. See, diagrams are represented. In the molecule 3 atoms are there, that these are along the one axis only, that's why taken linear molecules. Linear molecules of triatomic gas molecules also have the 2 degree of freedom only. See, clearly highlighted, student. Okay, now I am going to explain about this is the diatomic molecules. See there, now it is rotating along the y-axis. So whenever it is rotating along the y-axis, like this possibility is there. See there, student, y-axis rotation is like this is there. Okay, so that here radius is maximum for the diatomic molecules, that's why moment of inertia maximum, it will have the maximum rotational kinetic energy along the y-axis. And also z-axis also clearly represented. See there, z-axis, but this is triatomic molecule. See there, so in this also this is the z-axis. Now z-axis is rotating, that molecules also rotating 3-dimensionally, clearly we can represent. That's why here diatomic molecules and linear triatomic molecules have 2 rotational degree of freedom. This is clear diagram and explanation about the diatomic and triatomic gas molecules. Here triatomic gas molecules also represented along the x-axis rotation, radius is minimum, moment of inertia also minimum, so that I minimum because of m r square, radius is minimum, and rotational kinetic energy along the x-axis is 1/2 I omega x square. So this is also become very less. Okay, and rotational energy, that is rotational degree of freedom along the y-axis is clearly represented, and along the z-axis also represented for the triatomic gas molecule. 1 second, I will replace the paper. Now I am going to explain about the non-linear molecules, that is triatomic molecules. Previous also we did triatomic linear molecule. Now I am going to explain non-linear. Linear is along the straight line, non-linear is like this represented. See student, best example is hydrogen. This is represented, okay, O, and this is H, and this is also H represented. So that, see, the diagram already clearly taken there. O is the oxygen and hydrogen. Now it is rotated along the x-axis, like this it is rotating, student, along the x-axis. Okay, and along the y-axis rotation taken, and also z-axis. So along the y-axis rotation is like this, student, along the y-axis rotation is like this possible. Okay, and along the z-axis is like this rotation is possible, student, along this z-axis. See there. Okay, for non-linear triatomic gas molecules, we will get 3 degree of freedom, that is rotational degree of freedom. Remember, clear diagrams is taken for the hydrogen H2O. Okay, so physically I gave you one example diagram, okay, with representing balls and also represented diagrams. And next one is here triatomic gas molecule taken, that is SO2. This is also non-linear. Next one is tetraatomic gas molecule taken, that is NH3 along the x-axis, y-axis, z-axis, there also x-axis, y-axis, z-axis rotation, and polyatomic gas molecules taken. And next one, vibrational degree of freedom I am going to explain. See students, for the vibrational degree of freedom, the atom of molecule can also vibrate mode of degree of freedom, slightly change the internuclear distance between the atom of the nucleus. In the bond structure of molecule behave like a spring in simple harmonic motion. Nothing but like this we can consider there. The molecules are okay, between them taken a spring like example. The molecules are moving. In the molecule, the atoms are moving away and also the molecules are come close to each other. Okay student, in the vibrational degree of freedom, the atom of molecule can also vibrational mode of degree of freedom, slightly change the internuclear distance between the atom of the nucleus. In the bond structures, the molecules behave like a spring in a simple harmonic motion. So there are atoms which are stretching like this from the spring. Okay, so there are two atoms are connecting. For hydrogen taken, this is one hydrogen, this is another hydrogen, so that they are getting close together and moving away. Here both atoms, see there, moving away and close together in linear vibration. See, clearly represented in the diagram. Okay, this is in simple harmonic motion. Example is hydrogen taken. Okay, atom possess only translational motion degree of freedom. This is the example for the linear molecules. And next to taken non-linear molecule, for example H2O, hydrogen moving towards the O and another hydrogen is moving away from the O. Like this the vibrations are takes place in the non-linear molecules. But notice that at room temperature there is no vibrational degree of freedom. Okay, notice again, so that at room temperature there is no vibrational degree of freedom. And for first one, linear molecules, there is one formula to notice the vibrational degree of freedom. For linear molecules, 3n minus 3 translational plus 2 rotational degree of freedom. N represent the number of atoms. For example, triatomic gas, so in which n is equal 3, diatomic gas, n is equal to 2. Okay, and continuation there. Here vibrational degree of freedom, that is for the linear molecules, 3n minus 5 representing at the high temperature, this 5 representing 2 translational plus 2 rotational degree of freedom. And also next node 2 representing for non-linear molecules, that is 3n minus 3 translational plus 3 rotational degree of freedom, so that Fe representing 3n minus 6, n represent number of atoms. It is also possible at high temperature. Okay, room temperature we will not consider the vibrational degree of freedom. Okay, at high temperature, that is 3000 Kelvin and above only we will consider the vibrational degree of freedom. So node 1 represent the linear molecules. Formula for the vibrational degree of freedom, that is 3n minus 5. Here 5 represent 3 translational and 2 rotational. And node 2 represent for non-linear molecules, that is 3n minus 3 translational plus 3 rotational, that is Fe, which is equal to 3n minus 6 representing. So next one, law of equipartition of energy. It states that the total energy of molecule is equally distributed in all possible energy modes like translational, rotational and vibrational. So here we have translational motion, one translational degree of freedom, ut is equal to half kT. K is the Boltzmann constant, T is the temperature. 1 rotational degree of freedom, ur is equal to half I omega square. I moment of inertia, omega is the angular velocity. 1 vibrational degree of freedom, so that uv represent 2 into half kT. 2 we are considering because of vibrational motion of two atoms, oscillation against each other, that's why twice taken, so that 2 into half into kT. 2 also get cancelled. Wait a second. Yes, law of equipartition of energy, in which translational energy and rotational energy, vibrational energy just for one atom is given. Now I am going to discuss about the translation motion energy. Already this proof of pressure equation we did, and I will provide that video link in the description. So pressure P, which is equal to 1/3 mNv into V square R.M.S. See student, P represent pressure, M represent mass of the each molecule, okay, N represent the number of molecules, V is the volume, and V R.M.S. represent root mean square speed. Okay, so modifying this equation, see there, so 3PV divided by N, okay, is equal to mv square R.M.S. both side multiplied by half, 1/2, that is, so PV is equal to nRT, 1 mole of gas considering, so that PV is equal to 1 RT. So instead of PV I am replacing RT, clearly represented there, and R is equal to, we can write NK student. N is the number of molecules, that is Avogadro number. K is the Boltzmann constant, so that Nn is get cancelled. So I am getting there half m V/R.M.S. square, which is equal to 3/2 kT. So that is equal to kinetic energy translation motion, which is equal to 3/2 kT. Okay, so for monoatomic gas it has 3 degree of freedom, so that average kinetic energy per degree of freedom is Kex is equal to half kT. Next, second one is also we can write Key is equal to half kT. Third one also we can write along the z axis is Kez, which is equal to half kT. So that finally I am writing kinetic energy translation along the x-axis, y-axis and z-axis also, but the motion is same along the x-axis, y-axis and z-axis, magnitude is considering, so that translational kinetic energy, which is equal to half into kT for the x-axis, half into kT for the y-axis, half into kT for the z-axis, so that total value which is equal to 3/2 kT. So this is clear proof for the translation motion energy for the law of equipartition of energy. And also next we will have rotational motion energy, so that in this first one note 1 is given, and that is for diatomic and triatomic gas molecules, that is especially for triatomic linear gas molecules considering, so that Er, which is equal to half I omega square plus half I omega z square. See, x-axis 0 given, and also y-axis, z-axis, rotational kinetic energy represented. Proof already we did, just now completed. Okay, and next one, note 2 representing triatomic and polyatomic nonlinear molecules which have rotational degree of freedom along the x-axis, y-axis and also z-axis. Okay, and comparing to the rotational degree of freedom for the linear molecules, it has only 2 rotational degree of freedom. For non-linear molecules we will have 3 degree of freedom, clearly represented in the note 1 and also note 2. And third one is vibrational mode energy at low temperature, room temperature, many times repeated, no vibrational mode of energy because of there is no vibrational degree of freedom. Okay, at high temperature, 2 conditions considering for linear molecules, So F is equal to 3n minus 5. So energy EV we represent vibrational, that is 2 into 3n minus 5 divided by 2 into kT. 2 also get cancelled. So I gave you basic equation based on U is equal to F by 2 kT. Student, F is the degree of freedom for the linear molecules and 2 is taken, so that twice taking because of it has the kinetic energy and also potential energy in the vibrational degree of freedom. And next one, non-linear molecules taken, F is equal to 3n minus 6, also clearly given EV which is equal to 2 into 3n minus 6 whole divided by 2 into kT. Formula explanation already completed, just again writing about the high temperature linear molecules and also non-linear molecules, student, so that the energy associated with each degree of freedom is U is equal to F by 2 kT. So I am going to explain this energy mode with respect to constant pressure and also constant volume. So basic equation, U is equal to F by 2 kT, that is energy associated with each degree of molecule. For n molecules we will get NF degree of freedom, so that equation is modified, U is equal to NF by 2 into kT. Okay, but NK represent the capital R, so that U is equal to F by 2 RT is the first equation for the energy. And molar specific heat at constant volume, CV is equal to du by dt. So CV which is equal to U value replaced F by 2 RT, so that I am getting there CV which is equal to F by 2 R. This is taken as equation 2, clearly written perfectly derivation. Molar specific heat at constant pressure considering Cp minus Cv is equal to R. So Cp is equal to Cv plus R. Cv value is F by 2 R replaced there, so that Cp is equal to F by 2 plus 1 into R. R taken common is equation number 3. So that energy is equal to F by 2 RT, Cv is equal to F by 2 R and Cp is equal to F by 2 plus 1 into R. So the ratio of molar specific heat, gamma representing, gamma is equal to Cp by Cv. Okay, Cp value and Cv value replacing, so that we are going to get gamma is equal to 1 plus 2 divided by F. Okay, see there. First one, monatomic gas. So taken room temperature, example is helium, neon, argon, krypton. So degree of freedom 3, that it has only translational degree of freedom. There is no rotational degree of freedom for the monoatomic gas. There is no vibrational degree of freedom for this at room temperature and also high temperature. So that total degree of freedom written, that is 3 only. It has only translational degree of freedom, so that U is equal to energy F by 2 RT, so that F replaced by 3, we are getting 3 by 2 RT, and Cv is equal to F by 2 R. Proofs already we did, so that F replaced by 3. Okay, Cv is equal to 3 by 2 R. Cp is equal to F by 2 plus 1 into R, so that F by 2 plus 1, F is equal to 3, so that 3 plus 2 divided by 2, that is 5 by 2. Gamma is equal to Cp by Cv, so that 5 by 3, that is equal to 1.66. Okay, and diatomic at room temperature, linear considering, that is H2, N2, O2, CO2 and Cl2, F2 also, so that it has the 3 translational degree of freedom. Everything, that is di, tri and also mono and also tetra polyatomic gases, it has 3 degree of freedom, translational degree of freedom, and rotational degree of freedom will be changed, so that room temperature and high temperature for the diatomic gas we will get. So already we did, that is 2 degree of freedom, rotational degree of freedom. So that here we are going to get room temperature and also high temperature. Room temperature, there is no vibrational degree of freedom. High temperature, there is a formula, N is the number of atoms, that is clearly written for the linear 3n minus 5, for non-linear 3n minus 6 vibrational degree of freedom. So that here 5 represent 2 plus 3, that is 3 translational and 2 rotational. Already we did in the previous part. So that Fe is equal to 3 into 2 minus 5, which is equal to 6 minus 5 is 1. Okay, so that high temperature linear molecule of diatomic gas, 1 degree of freedom of vibrational mode. Okay, so that total degree of freedom is translational 3, rotational 2 and vibration is 1, so that which is equal to 6 degree of freedom. This is already we know, so the method is same. Okay, so gamma is equal 4 by 3, that is 1.33. Here gamma is equal 7 by 5 for the diatomic molecule at room temperature. So that notice clearly, that is diatomic or triatomic or monoatomic gas at what temperature, room temperature or high temperature, is a linear molecule or non-linear molecule. Okay, so based on that prepared this tabular form. Okay, and next one, triatomic gas molecule taken. So that room temperature, next high temperature taken. So that in triatomic gas molecules we have linear molecule and non-linear molecule. Linear molecule also taken at room temperature and high temperature. Non-linear molecules all are taken at high temperature only. Okay, but at room temperature there is no vibrational degree of freedom. Remember, room temperature Fe is equal 0, Fe is equal to 0. Okay, so the triatomic gas molecules here taken for linear molecules are CO2, N2, CS2 only. Okay, for this translational degree of freedom is 3, rotational degree of freedom is 2. At room temperature there is no vibrational degree of freedom, so that total degree of freedom for the linear molecule, okay, 5 only, 3 plus 2. So this is same method already we did. And next one, high temperature considering linear, so we are getting vibrational degree of freedom. So the formula is for this 3n minus 2 plus 3, that is 2 rotational and 3 translation. So formulas clearly given there, so I am going to get there 4 vibrational degree of freedom for the high temperature for the linear molecules, that is triatomic gas molecules. So total degree of freedom is 9 degree of freedom for the CO2, N2 and CS2. Okay, energy is equal, degree of freedom is 9 replaced here, also CV. Okay, F replaced by 9 and Cp is equal 11 by 2 and gamma is equal 11 by 9, that is equal 1.22, clearly written. And high temperature non-linear triatomic gas molecule taken, H2O already given information, yes, O2 also taken. It has non-linear, 3 translational, 3 rotational and vibrational degree of freedom, that is 3n minus 6 for the non-linear. Linear is equal 3n minus 5, so that 3 plus 3 is 6, that is 3 translational, 3 rotational degree of freedom. Please try to understand the tabular form, very easy, clearly given. So that here total degree of freedom 3 translational, 3 rotational, 3 vibrational, total 9, also repeated same way. And also tetratomic gas, high temperature NH3, okay, and CO3 taken. So that here vibrational degree of freedom Fe is equal 4 atoms are there. So the formula is 3n, n replaced by 4. So 3 4s are 12 and 3 plus 3 is 6. 12 minus 6 is 6 degree of freedom we are getting. So that 6 plus 3 is 12 degree of freedom. Okay, and F value is replaced in same way. Okay, and polyatomic gas, okay, that is taken best example CH4, that is non-linear molecule, high temperature. Okay, and Ft same only, and Fr non-linear, 3 rotational degree of freedom. Here basic formula 3n minus 6. So n is equal 5, 3 5 is 15, 15 minus 6 is equal 9 degree of freedom. F is equal to 9 plus 3 plus 3 is 15. So F value is replaced with gamma is equal to 17 by 15, 1.33. Okay. Please do like and subscribe our channel Nature of Physics.